In this video, we'll be dissecting the Malware Lab, and I'll be performing my analysis based upon the scenario that was presented. Now, in this example, we're presented with an IDS alert, and this is a very common workflow for a security practitioner, particularly a defensive security practitioner, one who might work in a security operations center, whose responsibility is to receive, parse, and investigate alerts from intrusion detection systems. Now, in this case, our alert is in a pretty standard format. It's either the snort or suricata format, both very popular signature-based intrusion detection systems. And what this is telling us is that it has detected that a specific rule related to the CyberEye rat has been fired, and something has been detected related to that type of activity. In this case, RAT stands for Remote Access Trojan, and it looks like our rule is detecting the session establishment related to the CyberEye rat. CyberEye, of course, being a particular variant of a rat that some bad guys are out there using somewhere, and we have a signature for. So we have this particular alert gives us a little bit of detail here. It tells us the timestamp, of course, and it tells us the alert was detected, traffic from 172.16.0.111 to 172.16.0.114. Now that's the direction the signature was developed to attack, so that doesn't mean that the traffic was sourced from the .11 address, not at all, but that's just where the detection occurred. Now we're provided with a bit of additional information related to the protocol, so we see some TCP information, some IP length information, sequence numbers, acknowledgement numbers, and so on. So that information is provided with the alert. Now, one thing we want to look at with the alert too is the signature that made it fire. This is the signature that was programmed to detect this specific anomaly. We have that signature, or the rule in that case, here, and this is in the snort or suricata rule format, and I'm not going to go through that in depth, but I will break this one down very simply. In this case, this rule tells us to alert on any TCP communication from anywhere in any port to our home net on any port. So that means it's coming from anywhere, whether inside the network or outside the network, but specifically to a device in our home net. And our home net is basically a simple way of saying IP addresses we're responsible for the security of. Now, when that happens, we are given the message, CyberEye rat establishment, that we've seen. And then we get to the actual meat of the rule, which is this content match. And this is a very simple rule. Rules can get much more complex, but this is a very simple content match for a string of hexadecimal characters. And you know it's looking for hexadecimal because the pipes are used. So we see the pipe symbol after it says content, 414E, 4142, 494C, 4749, 7C. So those are all hexadecimal characters, and then another pipe symbol. If those pipe symbols weren't there, it would be looking for just normal ASCII characters. But since it is there, it's looking for hexadecimal, that specific hexadecimal string, and apparently that's what we found. Beyond that, we have some additional metadata related to the signature. We see it's associated with the class type of Trojan activity, which makes sense. It's CyberEye rat is a remote access Trojan. It's given a specific SID, which is the unique identifier for the signature, and the revision of the signature, which in this case was revision 2. So this gives us the information we need to start looking at the packet capture that we have that was collected from our sensor in relation to this signature firing. I've opened the file malware2.pcapng to begin the analysis, and the good thing about this scenario is it's very realistic in that I have an IDS alert to go on, and it told me that I'm looking for a very specific content match. So I have a lot of packets here. I have 779 packets here, it looks like, and that's a lot. I'm not just going to go through this manually and go through every conversation. So this is much more like a realistic scenario in which I have more packets than I know what to do with, so I have to be a little bit more creative in my analysis. The good thing is I have alert data to pivot on, and that's really what investigations are all about, is looking at what data you have, asking good questions, and then pivoting based upon that data through other data sources into different sections of those data sources, and that's what we're going to do here. So what I'm going to go ahead and do first, let's go to edit and find packet, and I'm just going to go in here and paste in this hex value that the signature was looking for, and I've set this search area to look at hex values. Note that if I have this set as a display filter, that it will tell me it's invalid. I'm actually looking for that specific hex value. Now, if I hit find, I'm going to find that pretty early on. Matter of fact, it looks like I found an example of that in packet. Looks like packet 4 here. We see the hex value here, and it's highlighted here. It looks like it actually translates to ASCII text, ANABILGI. That's interesting because not all the time do these things translate to clear ASCII text. So that may be significant. Just to keep checking here, let's see if we find that anywhere else. I'll click find again. And what do you know? It looks like we see it here in packet 5, packet 10, 32, 156, 280, 405, 531, 652, and that's it. So we see it in quite a few places. So this that signature probably fired a few different times, or at least grouped multiple alerts into one execution of the alert. So we see that that's interesting. This string occurs time and time again, and that's something to keep in the back of our minds. That the string keeps occurring. That might be relevant to how it's used, and of course that's what we want to figure out, is exactly how this string is used, why it's relevant, because we know it's related with a remote access Trojan, which means there's a chance this could be related to some type of command and control, an attacker issuing commands against the system, and the repetitive nature of that command, it may be some type of heartbeat, some type of check-in, or maybe a specific command itself. Now, I want to go ahead and do something else which is interesting here. And remember, I noted that this hex translates to actually readable text, this ANABILGI. So that's interesting to me. And anytime I see a clear text string like that I don't immediately recognize, I'm actually just going to Google it just to see if I find anything that is useful to me that might help lead me down the right path in the investigation. So I've got Google open here. Let's just go ahead and just do a search for this text. ANABILGI. Let's go ahead and see if it comes back with anything that is interesting. So I just did some searching here, and I don't see anything that looks immediately useful here. So I'm going to go ahead and, what do you know? What's this? It looks like it says we have a translation here, English translation from a Turkish English dictionary. So that's interesting. I don't want to click on that link. I don't really know what that link is. But I tell you something I can do is go to translate. Whoops. I need to learn how to spell translate.google.com. And let's see if it is actually something that can be translated. Now, I go back here, and it looks like there's a space here. It looks like ANABILGI. So maybe there's a space, so maybe those are actually two words. So let's put that in here and translate it. And what do you know? Google Translate tool is great. It detects that it's actually Turkish. It detected that and decoded it to English in the word main information. So I don't really know what that means specifically. I don't know what to do with that right now. But it is interesting that word, which may be a command of some type, is translated to main information. So maybe it's a command being issued to retrieve some information about the system. Maybe the system's infected, and that's what the malware is doing. At least that's my working hypothesis. So that's interesting. With that information, we can pivot back to the packet capture and continue our investigation. So back to my capture file, I need to do a little bit more analysis. And we saw that the string we looked at appeared in a lot of places. And just kind of casually looking, it looks like we have mostly the same two IP addresses talking to each other. We have a 172.16.0.114 address and a 172.16.0.111 address. So we're looking around here. It looks like it's just all TCP communication. I don't see anything that's being decoded at a higher protocol level. I mean, we can go in here to the protocol hierarchy and look at it, and it's pretty straightforward. It's just all TCP packets and all TCP data, so we don't really have a lot to go on from a protocol perspective, not like we did in another example where we had HTTP data. So let's go ahead next and kind of enumerate the conversations that are going on and see if there are more than one. And it looks like in this case, we do have just two IP addresses talking to each other, 172.16.0.111 and 172.16.0.114. They're transferring a fair bit of data, 558,000 or 558 kilobytes, but we do have different communication or different conversations going on. It looks like we have 8 of them here, and that's interesting. So let's maybe break this out by different conversations and analyze those one by one. There's not too many of those here that we can't do that, and it looks like they're all probably related. It looks like we're all talking on the same port here. It looks like different source ports, but port 4433 is a destination port. It looks like all the traffic may be sourced from this 114 to the 111 address. So that's something we can work with. But to make that a little easier, let's maybe apply some colorization rules that may be a little bit helpful for visually discerning the difference between the different conversations, since there might be some overlap here. To apply those colorization rules, I'm going to do a little technique I like, where I'm going to look for all of the SYN packets used to create a network communication sequence. So I'm going to go ahead and go tcp.flags.syn equals 1 and tcp.flags.ack equals 0. And when I do that, it's going to give me only the TCP SYN packets using a Wireshark display filter. So we saw that there are I believe eight conversations, and so we have 8 of those packets here signaling the beginning of each one of those 8 conversations. And that's something I can actually work with my colorization filter. So I can go in here and right-click the first one, go to colorize conversation. We'll do it based upon the TCP conversation, and set it to color 1. I can do the same thing here. Colorize conversation, TCP, color 2, and I can actually continue to do that with each of these based upon the TCP conversation values. Of course, remember that in this case we're using the TCP conversation because we're concerned about the ports. We're not talking about the IP conversation, because these 8 different sequences would all be part of the exact same IP conversation, whereas they're part of different TCP conversations. And that's what we're interested in, because that's what's going to help us, give us a way to just analyze this a little bit more clearly and visually discern where these things start and begin, since after all they may overlap to some degree, and that can make the analysis a little bit more confusing. So I'm just about done here, and okay, looks like we are all colorized here, and each conversation is a different color. So now if I go here and clear my filter, we see that we can see clearly what constitutes a different conversation. So if you were just looking at these normally, you might think packet 5 and 6 are part of the same conversation because they're next to each other here, and if you just kind of casually glanced at it. But in this case, we see they're different, and we can also see in the bar here, we can see where different conversations start and begin. And I'll tell you, the first thing I noticed is we have this initial conversation here that's in this reddish color, and it looks like we have that right at the beginning of the packet capture, and then we have it sprinkled throughout it, and that seems to be a trend. So we have a bit of this red color, and then we have a different chunk of data, another conversation, a little bit more red, another conversation, a little bit more red, another conversation. That's really interesting to me, and as we continue to scroll, we see that continues several times. So we see a clear pattern emerging. We've done that simply by applying these color coding rules, and that's a pretty cool thing. So now that we have these colorized conversations, we can go ahead and start to analyze this thing a conversation at a time. So I'm going to go ahead and start here with the very first one. What better place to start, especially since it's the one that seems to be pervasive throughout the conversation or throughout the communication sequence, as we've already discussed. So I'm going to go ahead and follow the TCP stream of this data. That's all we can really do here to analyze the data, since we just know it's raw TCP. Now, when we open this up, we see a couple of interesting things, some familiar things as well. Now, keep in mind here that in this case we have two-way communication, and we have the client and the server, so to speak. So in this case, Wireshark identifies the client, as you see down here in red, and the server in blue. So the client in this case, we start with server communication, it looks like here. So the server sends this command, Anna Bilgi, and then a pipe and 556. And remember that this Anna Bilgi, and I'm sure I'm pronouncing that horribly wrong, but it's Turkish for main information. So we see that somebody is sending this to a victim in this case. This is coming from the more remote, or what we believe to maybe be the attacker system, and it's being sent to the victim. And we get a response here in this case from the victim. It looks like it echoes the same command, this Anna Bilgi. And then we see some system information being sent. So it looks like we see, in this case, some IP address. Looks like we have US, maybe that's United States. Administrator, it's probably a username. We see what appears to be maybe a computer name, C Sanders 6F7F77. We see an operating system, Windows XP Service Pack 3, and some more basic system information about the processor and memory and so on. So it appears that what we have here is probably a command being issued. So this main information command is being sent to the victim. The victim responds with what I guess constitutes main information. So that's sent to the system. now, or to the what I presume to be the attacker in this case here. So now here we see more information sent from the victim, and we see another command being issued, and it's baglimi, and a question mark. And it looks like this is sent a few times. And so what this kind of makes me think of is polling, like it's polling for a command. We thought that might be the purpose of this anabilg command, but it wasn't. It looks like it's an actual command that does something else. So we see this baglimi command, and well, we already translated the first one, so maybe we can translate this one as well. So let's go ahead and let's try to do that here. So I'm gonna go ahead and get rid of this, type in baglimi. I don't know if that's one word or two. And it looks like here it's Uzbeki. It says right here is what it's detected. It's translated to the word subject, which may be interesting. The other was Turkish. So let's actually try to force this to decode as Turkish. And it says line which connect my. So this is maybe one of those words that isn't going to have a direct translation, but line which connect my. That seems reminiscent of something that might be used to say, tell me about the connection, or what is the line which I'm connecting with, or basically something that is designed to receive commands. That's kind of what I get out of this, a rough translation from Turkish to English here. So since the other word was Turkish, we believe, based on what Google's told us, it makes sense that this one is too. So line which connect my, basically what I get out of this is I feel like this may be some type of command and control sequence, and what we have here is the system, in this case our victim, polling for commands of what's next. Now the capture would be boring if we just saw this baglimi command over and over and over again, but we actually do see some commands, or what we think are commands, being issued. And here we see cap screen 60, and cap screen, well, that leads me to believe that this may be a screen capture command that's taking a screenshot of the system and sending it back. So we can actually evaluate this ourselves pretty easily. So what I'm going to do here, notice when I click these, it brings me to specific locations within the packet capture. I'm just going to go ahead and click this first one, which looks like it takes us to packet 27, which is where that is observed. I'm going to close this, and let's go ahead and clear out the filter here. And if I clear out the filter, notice when this data is sent, this cap screen command, you see it right here in a single packet, that the data is acknowledged, and that's where our next communication sequence starts up. So that's where we have another conversation occurring. So remember, we kind of have this main control channel open that's pervasive throughout the communication, as we see with these little red lines here. But then all of a sudden we have this command sequence, and it appears to be at least partially related to this cap screen command, and then we have additional communication occurring. Now the question would be, is if I go back here, let's follow this TCP stream again, and that was the first command. Well, let's go ahead to the second one. I'll click on that. We'll close it. So we've been identified packet 151 is where that command was witnessed, cap screen 60. You see it down here in the packet bytes window. If I clear the filter again, let's see if we have the same output. And sure enough, we do. Notice that this data is sent, it's acknowledged here, and then we have a new conversation starting. So clearly this cap screen 60 command, whatever it's doing on the endpoint workstation, it's actually initiating some type of additional communication that's occurring here. Notice from this, the command is being issued from 111 to 114. So that's from our attacker to our victim, at least as we perceive it now. And then it is the victim who is opening up a new communication sequence directly with the attacker. So it's starting and opening this channel 114 to 111. And we see that's a TCP connection. So we have a send SYNAC ACK through a handshake before data is transmitted in this case. So now we can actually go in and start examining those individual connections to see if we can find anything useful in those that might warrant further investigation. Now to examine this particular example or this particular section of traffic, I'm going to do the same thing I did previously, right? It's just TCP data, so all I can really do other than iterating through each packet individually is just to follow the TCP stream here. Now, we don't necessarily know if all of these individual sections of response to this cap screen command, we don't know if they're all the same, but we have to start with one, so I'm just going to start with this one, which is the one I happen to find here. It's the one that I've colorized purple. Now, if I follow this, we've got interesting data to be had. So we immediately see that we have this anabilg command sent again in this case from server to client, as Wireshark has identified it. So this is going from our attacker system to our victim system, and then we see this bunch of data. And look, this is all sent from the victim to the attacker, and there's a lot going on here. You can scroll and scroll and scroll and scroll. Now we get some clues as to what might be going on. For instance, we see the cap screen command again, which we believe, of course, is related to a screen capture because that's pretty clear. And then we also see cwindows JPEG event hook .dat. Okay, well, JPEG, that's interesting. And then that's when we start seeing this data that doesn't appear to make a lot of sense to us. Now, if you've done a lot of file carving before, and certainly we've talked about file carving previously in this course, you know that generally files are identified by what we call magic bytes, and those magic bytes identify a specific file type. Well, we see some of those here. We see JFIF, and that is, at least in ASCII here as we've displayed this, those are the magic bytes we would expect to see for a JPEG file. So this holds to our theory that this may be a command that instructs the malware to take a screen capture and transfer that back to the attacker. So we generally believe this is going to be a JPEG or image file. Now, how can we figure out what it is? Well, we have the data here, so we can carve it out. So let's actually do that. Let's actually carve out this file from the packet capture and see if we can figure out what this is. To make this happen, we're going to export the data we want, which is not quite everything we see on the screen. We actually only want the data sent from the victim to the server that actually constitutes what we believe is part of the image file. So we don't want this first line, for instance. So I'm going to go ahead and go down here to entire conversation and tell it to only give us the data going in the direction we want in this case. I'm also going to go ahead and tell it to save the data out in raw format. And we'll go ahead and click Save As, and we'll get this data onto the desktop. We'll just call it raw image.jpg. And let's see, we'll go ahead and hit Save. And now we can try to open the image up. So if I do that here, let's go ahead and open our malware folder where I have that and try to open this JPEG file and see what happens. Looks like Windows cannot open this file. So what's the reason for that? Why can't Windows process this file if we believe it's a JPEG? Well, one option could be that it's not a JPEG, but all signs point to the fact it is. So why can't it? Let's go ahead and look at this data and change it back to ASCII. Okay, here's the issue. The magic bytes and the actual relevant data for this image start around here. But we have these additional commands that were part of the malware command and control. This is what's preventing this from being open because we exported this in our raw data dump as well. This is something we don't want. So we actually have to continue doing a little bit more manual carving to carve this data out since this is a custom C2 protocol. Wireshark will automatically carve things out of things like HTTP transactions because it knows those protocols and knows how to dissect them. But Wireshark doesn't have a dissector for this specific protocol because it's custom. So we have to continue to edit that out manually, and we'll do that in this case with WinHex. So again, this is very similar to another example we did, and we'll just open the file and do our editing, in this case manually. And we can open the image file here, and there we go. Now we can start carving the data we want to remove from the actual file itself. The important question here is, how do you know what to remove? Well, there are a couple ways. One is you could have done this before and you could have known the file structure of a JPEG and know exactly what data needs to be removed. The other is you could just make a good guess. You could start here. We see we have all these commands here in the ASCII representation, so highlight all those and go maybe as far as to here. That seems pretty straightforward, but then you'd actually still be missing a byte. You want to clear this extra byte here. So generally my best way to describe the best way to figure out how to know where to carve and where not to is if you believe you already know what the file type is. So in this case, we believe it's a JPEG file. Open up a legitimate JPEG file and see what the beginning and the end of that file looks like. If you can do that and then compare it to this one, you'll know exactly how far you need to go with your carving. It may take a little bit of experimentation, a little bit of trial and error, but by comparing what you think the file is to a perfectly normal or an exemplar of that type, then you can base your data on that, or your carving on that, and that's a good way to go. So in this case, I'm going to go ahead and cut out this data and save the file. We say yes, we want to update it. And now let's see if we can actually go here and update and open this file with the image viewer. Hey, how about that? It looks like we could. So now this is the image, and sure enough, it's exactly what we thought it was. It's a screenshot of the desktop of our victim. Of course, our victim looks like they have some juicy files on their desktop. We have the good old passwords.txt, salesorders.txt, and notes.txt. So this is a screenshot, and what the attacker was doing in this case was issuing commands via this malware that's installed on the system, and one of those is to capture the screen, an image of the screen, and transfer that back. So that's exactly what we've been able to observe and capture is the exact same file that was sent back to the attacker. So that's pretty cool, and that's a really neat example of carving files based on a custom protocol. It's a very simple one, but a very practical one as well. You'll have to do this often if you're analyzing malware C2 as part of your daily job. So that's going to do it for the analysis of this capture. That's really everything there is to see. Each one of these streams, these conversations we see, notice they're about the same size as relatively displayed on this bar. They're really the same thing. So as every time the attacker issued the cap screen command, a new communication sequence was opened up between these two systems, and a screenshot was taken on the screen and transferred back to the attacker. So you can actually go through and look at any of these and try to carve out the file. I will say for the purposes of this exercise, they're the same. You're not going to find anything in the other screenshots that you didn't find in the one I opened. They're all the exact same. So unless you just want some practice on it, there's not necessarily a need to do that. But let's recap a little bit about what we did here. Now we had an IDS signature that matched some traffic and alerted on it. So we took what we knew from the IDS signature and did a search for it. We just did a simple find for it, those hex bytes in the capture file. We found out that those mapped to what looked to be some clear text ASCII that we could do something with. So we Googled that, didn't find a lot, but did find that it looks like it might have been Turkish. So we translated that from Turkish, learned a little bit more about the command structure, made some hypotheses, and then we decided to go back into the packet capture and examine that a little bit more in depth. We looked at the protocol hierarchy. There wasn't a lot to see there. So we looked at the conversations and saw that we only had 2 IP addresses we were dealing with, but quite a few more TCP conversations. We colorized those so that they were quite a bit easier to see. That's the artifact of that, which we have on the sidebar here. We made the observation that there appeared to be one main communication sequence that was persistent throughout the file, through the packet capture file, so we examined that first. From there, we were unable to uncover that there did seem to be a clear sense of commands being issued and responses that were coming back, and from there, other connections were spawned. We examined a few of those other connections that were related to the cap screen command, and then we were able to determine that a screen capture was being initiated by the malware and transferred back to the attacker. So that was kind of our overall investigation process. This is a scenario where we're lucky that this was all in clear text and none of it was encrypted. Had this been encrypted, had the commands been encrypted, we would have had a much harder time not only detecting this because our signature wouldn't have worked, but also analyzing it as well. So that would have made things a lot harder. Nonetheless, this is a common command and control sequence. A lot of malware operates the exact same way as what we just examined here. This was real malware I used. It was taken from a sample, and I actually installed it, and I installed it in a lab, and I was the attacker and the victim at the same time. But this is real world malware and a real world example of malware command and control. So I hope this exercise was useful to you. We got to do a little bit of file carving, a little bit of broader analysis than just scrolling through every packet capture in the file. And I think this is a good continuing introduction into using packet analysis for the examination of malware.